Work, energy, and power. You probably use these words all the time, right? But what if I told you that in physics, they mean something incredibly specific and completely connected? Today, we're going to peel back the curtain and see how these three ideas are the engine that runs pretty much everything that moves in our universe. So let's just jump right in with a little thought experiment. Picture this. A porter is lugging a super heavy bag through a train station. He's walking horizontally at a steady pace. I mean, you can see he's sweating, his muscles are straining, he's clearly working hard. But in the world of physics, is he actually doing any work on that bag?
The answer is probably not what you think, and honestly, figuring out why is the key to unlocking this whole topic. So stick around because we're about to solve this little mystery.
Okay, so first up, what even is work? In our everyday lives, work is anything that makes us tired, right? A tough day at the office, a hard workout. But for a physicist, it's way, way more specific than just effort. For work to happen, you need two things, no exceptions. First, you need a force. And second, that force has to actually make the object move. It has to cause a displacement. So you can push on a brick wall with all your might, and you'll get tired for sure. But if that wall doesn't budge, sorry, but in physics terms, you've done zero work. Now, here's where it gets really interesting. Look at the full formula. It's not just force times distance. There's this little extra piece, cosine of theta. That theta, that's the angle between the direction you're pushing and the direction the object is actually moving. And trust me, that angle changes everything. This angle basically gives us three flavors of work. If you push a box forward and it moves forward, the angle is 0. That's positive work. You're adding energy, making it speed up. Now, if something is sliding towards you and you push against it to slow it down, that's a 180-degree angle. That's negative work. You're removing energy. But what about that 90-degree case? And we're back to our porter. Think about it. Which way is he applying force to the bag? He's holding it up, fighting against gravity. But which way is the bag moving? It's moving forward with him. The angle between the upward force and the forward motion is a perfect 90 degrees. And what's the cosine of 90? It's 0. So all that effort, the work he's doing on the bag, is a big, fat 0. Mind-blowing, right? So if work is the action, what allows the action to happen in the first place? Well, that would be energy. The best way to think about energy is like it's the currency of the universe. You can't do any work without spending some energy. And this currency mainly comes in two forms, at least for our purposes, kinetic and potential. Kinetic energy is the energy of stuff that's moving. Potential energy, on the other hand, is stored energy. It's the energy something has because of its position. Let's look at kinetic energy first. It all comes down to two things, an object's mass and how fast it's going, its velocity. But look closely at the formula. The velocity is squared. That's a huge deal. It means if you double your car's speed, you don't just have double the energy, you have 4 times the kinetic energy. It's why speeding is so incredibly dangerous. And you know, what's cool about a formula like this is that it's a two-way street. If you know the energy and the speed, you can figure out the mass. If you know the mass and the energy, you can find the speed. They're all totally interconnected, which is what makes physics so powerful. Now for potential energy. This is basically energy in waiting. When you lift a heavy book off the floor, the work you do against gravity gets stored in that book as potential energy. It's like you're putting energy into a savings account, ready to be cashed out later as motion. Okay, so we've got these two types of energy, but they don't just exist in their own little bubbles. They're constantly talking to each other, trading places, all governed by one of the most important fundamental rules in all of science. And here it is, the law of conservation of energy. It's simple, but profound. It just means you can't make energy out of nothing, and you can't get rid of it. You can only change what form it's in. The total amount of energy in the universe is always the same. A roller coaster is the perfect example of this. Picture it. At the very top of that first big hill, the car is barely moving. It's loaded with potential energy, but has almost 0 kinetic energy. Then, as it starts to fall, that potential energy gets converted into kinetic energy, speed. At the very bottom, it's going its fastest. It's got max kinetic energy and almost no potential energy. Then it all converts back again as it climbs the next hill. It's a beautiful dance. So we know work needs energy, and we know energy can change forms. But what's the actual direct link between them? How does work actually work? Well, that's where something called the work energy theorem comes into play. This is the big connection right here. The theorem says that work is the act of changing an object's kinetic energy. It's not just a number you calculate, it's the physical transfer of energy. When you do positive work, you increase its kinetic energy. When you do negative work, you decrease it. It's that simple.
Think about pushing a friend on a swing. The work you're doing with each push is directly adding kinetic energy to them, making them go higher and faster. You are literally transferring your energy to them through the act of work.
We're on the home stretch. We've got work, we've got energy. There's just one last piece to this puzzle. It's not just about how much work you do, but also about how fast you do it. And that, my friends, brings us to power.
Power is all about timing. It's work divided by time. So a powerful engine isn't necessarily one that can do a lot of work, but one that can do a lot of work in a very short amount of time. It's the rate of energy transfer that counts.
Here's the most intuitive way to think about it. Imagine you have to climb a flight of stairs. Whether you walk up slowly or sprint up, you've lifted your body the same distance against gravity. So you've done the exact same amount of work. But which one feels harder? Running, obviously. That's because you did the same work in less time, which required a whole lot more power. All right, let's wrap this up. What have we learned? First, work isn't just effort. It's a force causing movement in the same direction. Second, energy is the capacity to do that work, coming in two main flavors: kinetic for motion and potential for position. Third, that energy is always conserved. It just changes its outfit. And finally, power tells you how fast you're getting that work done. And that leaves us with one final question to chew on. We know a speeding car has a ton of kinetic energy, and we know that when the brakes slam on, that energy seems to just disappear. But we just learned that energy can't be destroyed. So where does it go? Think about that one.